Good day everyone, I am April Rose Forteza, and in this video, we are going to discuss the solutions to some selected items from the problem set. To start with, let's have this item number 2. In this item, we are going to perform the indicated operation on the following matrices. So we have to consider the following matrices to answer the following problems below and compute whenever possible. So in this, we are going to perform the indicated operations of the letter D. So in this letter D, we're going to perform the difference between 3D and 2E. So in here, we're going to focus on matrix D and E in order to perform this operation. So let's start with taking our matrix D and E. So we're going to perform the indicated operation. So we have 3D minus 2E. So now performing the scalar multiplication. So now we have this matrix. Then we can perform subtraction on both matrices. So we have 3 minus 12 is equals to negative 9. 15 minus 2 is equals to 13. 6 minus 6 equals to 0. Negative 3 minus negative 2 equals to negative 1. 0 minus 2 is equals to negative 2. 3 minus 4 is equals to negative 1. 9 minus 8 equals to 1. 6 minus 2 is equals to 4. And 12 minus 6 is equals to 6. So therefore, this is our final matrix. So let's have another item. So we have item number 6. Given the matrix below, determine the following cofactors and find its determinant. So here we select the number 4 Roman numerals, which is the A41. So before going to the process of our solution, let's just have the definition of a cofactor. So cofactor is written as Aij, where Ij is the subscript, I is the row, and J is the column. So the definition is that let Aij be an n by n matrix. So the cofactor of Aij is defined as Aij is equals to negative 1 raised to the sum of the row and column times the determinant of our minor matrix. So moving on to the process of our solution. So first we have to find our minor matrix, which is A sub 41. So this can be found by taking our original matrix, which is this one, and then let's get rid of our fourth row and first column. So we have the remaining entries. So this will be our minor matrix, which is A sub 41. So now we are ready to find the cofactor of that matrix. So we have to use this formula using the definition of the cofactor. So we have A sub 41 is equals to negative 1 raised to 4 plus 1 times the determinant of our minor matrix. So to obtain the determinant of our minor matrix, so we can use this pattern. So here we repeat the first and second column of our matrix A. Then form the sum of the products of the entries on the lines from left to right, and subtract from this number the products of the entries on the lines from right to left. So we're going to use this pattern to get the determinant. So upon plugging its values and computing it, we have the determinant of our minor matrix, that is negative 6. So now we can continue solving the cofactor. So we have A sub 41 is equals to negative 1 raised to 5 times negative 6 is equals to 6. So therefore, we have the cofactor of A sub 41 is equals to 6, and its determinant is negative 6. So now let's move on to our next item, which is item number 8. So in this item, we pick letter B, in which we are going to solve whether this vector is a linear combination of V1, V2, and V3. So before moving on to the process of our solution, so let's just have the definition of linear combination of vectors. So we have a vector V in a vector space. V is called a linear combination of vectors U sub 1, U sub 2, and U sub k in V if V can be written in the form of V is equals to C sub 1 times U sub 1 plus C sub 2, U sub 2 plus C sub k and U sub k, where C sub 1, C sub 2, and C sub k are scalar. So by the definition, first thing we have to do is to set a linear combination of these three vectors would look like. So we have C sub 1, V sub 1 plus C sub 2, V sub 2 plus C sub 3, V sub 3 is going to be equal to vector V. So to figure this out, we first put all these three vectors into one augmented matrix and use elementary row operation to convert the matrix into reduced row echelon form. So we already have our augmented matrix, and what we're going to do next is to set this into reduced row echelon form. So to start with, we want our first pivot entry in the first column here, or what we call the first non-zero value, is going to be 1. So to have our first pivot in column 1, so we take R1 divided by 4, so we get 1. So therefore, we have the new row 1 is going to be R1 divided by 4. So this is how it would look like, where row 2 and row 3 does not change at all. So now we have our first pivot entry, and we call that we want the value below our pivot entry is equal to be 0. So in order to do that, notice that in row 2, if we take R2 minus 2R1, that would be 2 minus 2 times 1 is equals to 0. And the same as in row 3, if we take R3 plus 3R1, so it would become 0. So therefore, our new R2 is going to be R2 minus 2R1, and our new R3 would be R3 plus 3R1. So this is how it would look like. So in here, the second row has all zeros. So we interchange row 2 and row 3. So this is how it would be. So now, we already have our first pivot entry had all 0 below. So the next thing we will work out is to our next pivot entry, which is the negative 1/2. We want this to be 1. So we take negative 2 times R2. So this is our new R2. So the last matrix will be already our reduced echelon form. So notice that we have a leading entries in column 1 and column 2. So we have x sub 1 and x sub 2 are leading variable. However, column 3 does not have a leading entries. So there it would be our free variable. So we can let this x sub 3 is equals to parameter t. So we have x sub 1 minus 2 x sub 3 is equals to negative 2, and x sub 2 plus 3 x sub 3 is equals to 6, where we let x sub 3 is equals to t. So now we get the parametric set of equation describing the solution space. So from the definition a while ago, V is a linear combination if it takes into this form. So working this out, we have, so using the scalar multiplication, we arrive into this one, and then performing addition operation, so we have this final. So notice that the right hand side and the left hand side are the same. Therefore, we can say that V is a linear combination of this vector 1, V2, and V3. So let's have another item, that is item number 9. In here, we are going to identify which of the following vectors in R4 are a linear combination of vector 1, V1, V2, V3, and V4. So in this item, we pick letter C. So in which we are going to solve whether this vector is a linear combination of V1, V2, and V3. So let's recall about the definition from the previous item about the linear combination of vector. So first, we set our linear combination of vector 3 of how it would look like. So this is it. So then we put all this into one augmented matrix and use elementary row operation to convert the matrix into reduced row echelon form. So we already have our first pivot entry, which is 1. So what we're going to do next is to set all values under the pivot equals to 0. So in doing so, we perform this operation, where the new R2 would be R2 minus 2R1, and the new R3 would be R3 minus R1. So this is how it would look like. So now let's proceed to our next pivot. So we want to convert negative 7 into 1. So we do this, we divide R2 divided by negative 7. And now this is how it would look like. So now we set all values below and above pivot into 0. So in order to do that, we take our new row 1 into R1 minus 4R2, and our R3 would be R3 plus 6R2, and then R4 would be R4 minus 3R2. So this is how it would look like. So in our third pivot, we want to convert 5 into 1. So we take our new R3 would be R3 divided by 5. So this is how it would look like. Now we're going to set all values above and below pivot equals to 0. So we take our new R1 into R1 minus R3, and our new R4 would be R4 minus 5R2. 5R3 rather. So now this is how it look like. So working on the last pivot, so we want this 10 into convert into 1. So we take R4 divided by 10. So this is how it would look like. So we set values above and below pivot into 0. So we have this. So we already arrived at our reduced row echelon form. So going back to the definition of linear combination, so V is a linear combination if it takes into this form. So working this out, so we check this if we arrive to our V. So using the scalar multiplications, we have this, and performing addition operation on this, so we have this. So notice that the right hand side and the left hand side are the same. Therefore, we can say that V is a linear combination of V1, V2, V3, and V4. So now let's have our last item, so which is item number 19. In here, we're going to find a basis for and the dimension of the solution space of the homogeneous system of equations. So here we pick letter A. So we set our augmented matrix and use the elementary row operation to convert the matrix into reduced row echelon form. So notice we already have our first pivot entry. So what we're going to do next is to set all values under the pivot equals to 0. So in doing so, we perform this operation where the new R2 would be R2 minus 2R1, and the new R3 would be R3 minus R1, and the new R4 would be R4 minus 5R1. So this is how it would look like. So working on to our next pivot entry, so we want this 7 into 1. So we take our new row 2 would be R2 divided by 7. So this is how it would look like. So now we set all values above and below pivot equals to 0. So in doing so, we have this new row 1 would be R1 plus 3R2. Our new row 3 would be R3 minus 7R2. Then our new R4 would be R4 minus 7R2. So this is how it would look like. So this is now our reduced row echelon form. So notice that we have leading entries here. So in column 1 and column 2. So we have x sub 1 and x sub 2 are leading variable. However, column 3 and column 4 does not have a leading entries. So therefore, it would be our pre-variable. So we can let this x sub 3 is equals to the parameter t s, and x sub 4 is equals to the parameter t. So we have this. We have x sub 1 minus 2 over 7, x sub 3 plus x sub 4 is equals to 0, and x sub 2 minus 3 over 7, x sub 3 is equals to 0. So, and we let x sub 4 is equals to t and x sub 3 is equals to s. So from this, we can express our equation into s and t. So now we get the parametric set of equation describing our solution space. So we have x sub 1 is equals to 2 over 7s minus t, and x sub 2 is equals to 3 over 7s. Now we can separate our equation for a vector. So this is what we're going to have. So separated our t, s, and t, and multiplied it by our vector. So therefore, the basis of our solution space are this one, and the dimension are the number of vectors in the basis for the solution space. Hence, the dimension of solution space is 2.